In 7.2, we will take a look at how we can use this information about the normal curve and use it to answer some actual questions, some applications specifically. And the first thing, easily the most important thing that we need to make sure we understand, is also, again, some review from chapter 3, where we learned this thing called the z-score. This is their basic z-score formula. Remember, z-score was the idea of measuring the position of a single number. So you could plug in any data value, subtract the mean, divide by standard deviation, and this number, as we saw back in chapter 3, represents something very specific. In fact, we had a word-for-word definition for this, which I'll remind you of. It was that the z-score represents the number of standard deviations away from the mean that data value is. So you find the difference, divide by a standard deviation, you get a number. Generally speaking, that number is between -3 and +3 because of the idea of the empirical rule that most values don't fall outside that range, especially for normal curves, normal distributions. But that's the idea. The z-score represents position. And so down here, just as a reminder, the idea that if you were to take effectively an entire data set, I don't care what data it is that has this distribution, if you thought about the z-scores of all the numbers, rather than labeling this axis based on whatever the units are of whatever your data set involves, if you labeled it based on the z-scores of the numbers, 0 would be the center, because if I asked you how far away from the mean is the mean, it's 0 away. Right? The standardization is the idea here, to standardize, to take any data set and describe it by z-scores, describing it where it relates to the center of your distribution being a 0. Well, then positives are to the right, negatives are to the left, and like I said, if you get to positive or -3, you're pretty much getting to the ends of that distribution if it's a normal distribution. But notice the z-scores, again, they tell you what's going on. They tell you if you had a z-score of 1, you know that z-score of 1 means 1 standard deviation, exactly 1 jump of size, whatever that is, to the right. If you have a z-score of -2, well, then you are 2 jumps, 2 standard deviations to the left. So the sign is very important there. But what makes this really important is we're going to use these z-scores in order to actually find the area under the curve for between any 2 values. So we're going to do so with our calculator. So this is where you have to have access to a graphing calculator with this stats command or stats function. The function is called normal CDF. Now, for the TI-83s and 84s, the way you find that, and the button's right here for you, you hit second, and this vars key, which is taking you to the distribution menu. And so it's got quite a list, and in fact, we've visited this list before in an earlier chapter. We went to the towards the bottom of the list and used things like binom, PDF, and CDF. But now, when I hit second in vars, I want the second option, normal CDF. So, whenever you're using this function, normal CDF, the way we want you to be familiar with it is that it requires 2 z-scores, a lower and an upper. Basically, the leftmost and the rightmost point of an interval that you want to look at the area between. Now, I want to point out that for the TI-83, whenever you click enter on this, you just get that prompt in an empty screen. So you have to know that that's what it wants you to enter, is a lower z-score and an upper z-score. For TI-84s, you're taken to more of a prompt-based screen. When you're there, I want to make sure that you are doing the same steps that we're doing here as we use the 83. So what I need you to do is for the 84, I'm going to put this off the side here, for a TI-84 or basically any graphing calculator that prompts you, you're going to have to make sure you tell the calculator that the mean is 0 and standard deviation is 1. We're going to eventually get to word problems that have information about a specific data set. We don't use their mean and standard deviation. We're going to make sure we convert everything to z-scores for the practice and for other purposes down the road. So enter these as your first 2 values of mean and standard deviation, and then it'll prompt you for your lower and upper z-score. Again, those of us who have TI-83s, we don't need to fill in that prompt. This function assumes it, and you just enter lower z-score, and then the comma, which is right there, and then upper z-score. So to get some quick practice with this function, because it'll be a function you use countless times between now and the end of the semester, The first way it's phrased is just this idea. Find the area under the normal curve between two values. So if I'm going between 1.2 and 2.3, then I need my normal CDF, 1.2, comma, 2.3. It's as simple as that. Once you've got that written out, we will enter that in our calculator. I've already got normal CDF up there. It's as simple as just typing 1.2, comma, 2.3 and hit enter. And so that number, it makes sense that it's a decimal because it's supposed to represent an area under this curve. And what I'm going to go ahead and do, unless the directions, say in my stat lab, tell you differently, I'm going to always suggest you take it to 4 places. We've talked about probability for a couple chapters, and I said that's a good amount of accuracy for probability. That's the main reason why I'm going to go ahead and use that for the amount of accuracy to kind of default to that. Now, the next one says less than 1.4. And we're not drawing pictures yet, but we will on the next page. But think about what that means. Let's go back up to this graph real quick. 1.4, it's over here somewhere. So less than 1.4 would be shading or thinking about everything under the curve to the left of 1.4. The problem is we don't stop at -3 because we said this curve does keep on going. It technically keeps on going forever. Now you can't input infinity into your calculator, but here's what we're going to do. And it's mentioned at the bottom of the page as well. If this is your z-score, -1, -2, -3, and we're already getting very close to the x-axis here. If you keep going out -4, -5, -6, this graph gets so close to the axis, there's no way you could even discern a difference to where the distance or area there is so minimal, it won't affect the answer at all. So I want to point out what I've got typed in your notes is almost an exaggeration even, where I'm going to say use -100 or +100 if there isn't a lower or upper limit. So in this case, it's less than 1.4. I'm going to do the normal CDF, but if I'm going left forever, I'm going to use -100 as that lower z-score boundary. Again, technically there's stuff beyond it, but that's low enough that if I say from -100 to 1.4, and we enter that into our calculator. So second vars, normal CDF. Do make sure that you use the negative button and not the minus sign when entering a negative number in your calculator. It will really confuse it if you don't. So -100, comma, we want to go to 1.4, and so I'm getting 0.9192 as an answer. And notice, let's go back to the picture for reference. That makes sense. 1.14 is way over here. This looks like the vast majority of the curve if I'm talking about everything left of 1.4, right? There's not a lot to its right. So it makes sense that this is a pretty high value. What I do also want to point out really quickly is I mentioned that this is really almost an exaggeration. I just want to point out what happens if you just put -10. Because even -10 is still a bunch of jumps to the left, right? 3 is almost done, and you're going 7 more out here. Notice that even if we do the same exact normal CDF, second vars, normal CDF, and do -10, comma 1.4, even changing that -100 to -10 to this many places of accuracy, right, to 10 places of decimal accuracy, they are still the exact same number. That's how small, that's how close to the graph, or to the axis, the graph is after you even get out 10 jumps to the left. Between 10 and 100 jumps, going 90 more jumps, doesn't add a single decimal to that probability or that proportion or that area up to 10 places, okay? So I'm also fine if you use -10. I put -100 in the notes. You're gonna probably notice me use -10 because I just kind of seem to default to that because I know there's no difference. But if that helps you remember the exaggeration of it and why we use it, then definitely use the -100. All right, so next page here. Again, kind of making the transition from just the question of area to the question of probability, which are the exact same question. Now the question of what's the probability that a z-score will be? So I've just changed the wording from area under the curve to working with a normal distribution. Probability is now the question, but it's the same question. So if I want at least -1.4, so now make sure we know what at least means. At least means this or more. So we're looking to the right of -1.4. I'll go ahead and draw a picture here. We're going to start drawing pictures almost constantly with this next example. But for this one, just to point out, again, what's happening if you've got a bell-shaped curve, well, we'll call that bell-shaped, normal, negative 1.4 is somewhere over here to the left, right? Maybe halfway between the middle and the end, or what looks like the end. Negative 1.4, the z-score, at least is looking at all of that, right? Everything greater than, beyond, to the right of negative 1.4. And so, to find that area, we will use our function normal CDF. And so, negative 1.4 is the lower bound. But if you're going off to the right forever, then we'll use the positive 100 for that. And so, if we enter negative 1, or normal CDF of negative 1.4, comma 100, I want to point out what we get, 0.9192. Notice you are getting the exact same number that we got when we looked at to the left of 1.4. The area, so again, because of symmetry, the area left of 1.4 is the exact same as the area right of negative 1.4. The more familiar you get with the bell-shaped curve and its properties, the more little things like that you can notice and use to your advantage. Okay, and the other one, the probability that a z-score is less than negative 0.4 or greater than 1.3. Okay, so for this one, again, let's draw a quick picture to help us see what's happening. Less than negative 0.4. So again, remember 0 is always your center, so negative 0.4 is not too far to its left. All right, negative 0.4, somewhere to its left. 1.3, a little bit further, but to the right of 0, so 1.3. But we're asking for less than negative 0.4, so we want all those values, or greater than 1.3, so we also want to include those. The way they ask this, they're basically asking for combining those two areas or those two probabilities, one or the other. Either one could happen, this plus this. Now, I like drawing this picture because we could absolutely answer these as two separate questions. I could make this a normal CDF of negative 100 to negative 0.4, and this normal CDF of 1.3 to 100. But we could also use to our advantage that we know the full bell-shaped curve has an area of 1. And if I want this and I want this, but I don't want that, we could find this area, the shaded area, by saying, what if we just took the whole area of the curve minus the part that we don't want? We don't want the area, probability, normal CDF, from negative 0.4 to 1.3. That's the unshaded area. Take it away from 1 and you will get the shaded area. So this is another, again, when you're familiar with the probabilities, just another nice little trick you can use when you're familiar with the characteristics, I should say, of the bell-shaped curve. So I'm going to go from negative 0.4 to 1.3 and find that that area, that unshaded area, is 0.5586 rounded to 4. And so subtracting that from 1 would be 0.4414. So again, just tricks you can use, not required. You could do it by hand, each one individually and add them. You get the same value. All right, one other quick note here, kind of breezed over. I didn't really mention it in the previous questions. The idea of whether or not these values, or if you want to call them the endpoints of these intervals, are included or not is actually arbitrary when dealing with this continuous data. So whether something says at least negative 1.4 or more than negative 1.4, whether or not you would include that number or not, there's no distinction. There's no way to distinguish that in your actual entering of the numbers or interpreting of the value. So either question, greater than or equal to, have the exact same answer theoretically with how we're using this process. So don't get confused or don't worry about, if there's a difference there, because there isn't. All right, so now getting us to why we want to be able to do this is we want to be able to use this to answer what I'll call actual problems with actual data. This is the process we're going to use. I'll just go ahead and jump into the example and we'll talk through what this is telling us we need to do. So here's our first example. The average commute to work is 25.5 minutes, according to the census. If commuting times are normally distributed with a standard deviation of 6.1, what's the probability a randomly selected commuter spends more than 30 minutes traveling to work? Okay, we want to break that information down. something that's not actually even in the steps, but I like to do anyway, is just pull out the really important things and identify them. The average commute is 25.5. Mu, in this case, is 25.5. Go a little further, I will point out we do need to see that. We need to know we have a bell-shaped normal curve. But then standard deviation of 6.1. So sigma 6.1. Those are both very important. Now the question, what's the probability a randomly selected commuter spends more than 30 minutes traveling to work? Okay, so the question of step 1, determine the probability you need to find. Draw and label a normal distribution in terms of your variable. That's what x represents, your actual numbers, your actual data set, and shade the appropriate region. Okay, so first step, we want to draw a normal curve, and what I'll call our first normal curve. I'll even label it x, because again, we're talking about what I'll refer to this quite often as we're in dealing with the data. So I'll call this data world. I'm not gonna always write it, but I'll use that phrase. We're in data world here. This picture exists in the data world of people traveling to work. What's that mean? Well, that means the 25.5 is the center. Now, if you wanna label that, you can. You don't have to, and sometimes I don't want to confuse you that we're gonna need that number necessarily, but it's important to know where it's at. 25.5 is here at the center. Why that's important is I want to draw a picture that represents the question of people that spend more than 30 minutes traveling to work. Knowing that this is 25.5 would tell me that 30 is somewhere to its right. Now, I don't need you to be accurate about it, but 30 is somewhere to the right of center. And I do want you to know and label that. Understand that much about it. That really will help. So there is the idea of 30's location to the right, and I actually are shaded in the idea of more than 30 minutes, right? That shaded region represents all the commute times that are more than 30 minutes above, right? Beyond 30 minutes. So that's our picture in, again, what I'll call data world, in the world of X. Now, step 2 says find the corresponding z-score or z-scores for the boundaries. Well, for this picture, there's only one known boundary, just that value of 30, so we will find a z-score of 30. So there's your z-score formula. 30 is your value of x. This is the value of your data. Oops, not an equal sign, that should be minus sign. Minus the mean that we know is 25.5 over the standard deviation of 6.1. This is why it's useful to have labeled that stuff right here, so you're ready to plug it into the formula. Now, speaking of plugging it in, if you're using a calculator, I just want to remind you, be very careful with the syntax on a calculator to enter this. If I type 30 minus 25.5 divided by 6.1, we're going to have issues, right? In fact, I'll do it, and we get that. That is not correct to say your z-score is 25, right? 30 is not 25 jumps away from the mean, right? We see that. We could understand that just by looking at the picture even. So what's wrong here? Your syntax is your calculator needs to understand to do that entire numerator first. Oops. And then divide by 6.1. So we would want to type it, if you're doing it in one step, that would need to be the way you enter it to get that value. Now, don't get confused here. You see a decimal, but remind yourself what this decimal right here, this number represents. It represents a z-score you're calculating, right? So don't let yourself think, I found the answer. I've got the probability, right? That's not where we're at in this problem right now. We are finding the z-score. In fact, I'm going to go ahead and round the z-score to 3 places, 0.738. It just kind of depends on my stat lab, what they're feeling like. It's either going to be 2, 3, or 4 usually. I don't like to use 4 because I don't want to confuse it with my rounding rule for probabilities. So I'm going to say 0.738 for the probability here, or for the z-score of 30. Now, what that means is with step 3, we're going to redraw our picture, but now think of it as if we're in the z-score world. In other words, we have now standardized the distribution. Remember, once we've standardized it, once we're in z-score world, our center is 0. And again, you can write it if you want. I'm not going to, but our center is at 0. This 0.738, though, it represents the exact same picture we drew here. If this is 0, 0.738 is to the right of 0, and we want to be shading the area to its right. I realize my curves don't look quite the same, but we're saying those two pictures should be identical. This picture and this picture, those shaded regions, the position of that line, those represent the same thing, a data value of 30 and a z-score of 0.738. And now that we've drawn this picture, we can say, let's find that area. Finding that area is now in z-score world. That's where normal CDF comes into play. Normal CDF of 0.738 going on to the right forever, so that's why we didn't need to find two z-scores. We can just go off to 10, positive 10, and see what we get there. Normal CDF of 0.738, comma 10, giving me 0.2303 when rounded, because that is the probability, right? Area under the curve, what comes out of normal CDF is the probability. Okay? And again, that just answers the question. 0.2303 is the probability a randomly selected commuter spends more than 30 minutes traveling to work.